Hello everyone, this is chapter 9 part 3. In this part we are going to put together isoquants and isocosts to find the profit maximizing input combinations. Okay, so we'll talk about cost minimization. Cost minimization while we find the optimal or the best capital and labor combination to produce what we want to produce. So let's say we want to produce Q0 level of output. Let's say this is profit maximizing. Okay, this is the desirable output level and you want to do it at the lowest possible cost. We can prove it using calculus or we can do it graphically. So I'm going to do it graphically. So labor x-axis, capital y-axis, this is my isoquant that I'm trying to reach, right? So there are lots of different these red isocost curves. So this is isocost number 1, this is corresponds to C0, C1, two different isocost curves. Actually there are infinite number of isocost curves. There are different cost levels in terms of production. Let's clean this. Okay, so a firm minimizes the cost of producing Q0 units, right? I'm trying to produce this by using the capital labor combination at point P. How did we find this point? We're looking at the tangency point between the isoquant that we are trying to reach and the isocost curve that is tangent to it. Remember, as you move away from the origin, the costs will go up, right? You're trying to find the isocost curve that is closest to the origin, right? But also achieves this output level. So the optimal point will be P, where your isoquant is tangent to this isocost curve. Okay, the lowest isocost curve. And point P will give you that optimal combination. You could put a star, K star, L star. Those are the quantities of inputs we should be hiring. Okay, all other combinations, all other capital labor combinations, for instance, point A or point B, lie on higher isocost. Okay, so point A or B will be more expensive. Another isocost curve, another point here, even more expensive. So I'm trying to produce, what I'm trying to do is that I'm trying to produce this level of output with the lowest possible cost, closest to the origin. So I'm going to grab the isocost curve that is tangent at one point to my isoquant. That's the optimal labor capital combination. At point P, the isoquant is what we call tangent to the isocost. So the slope of isoquant will be equal to slope of isocost. And what was this? Slope of isoquant, right? This one was negative of marginal product of labor divided by marginal product of capital. This was the marginal rate of technical substitution, negative of it, which is equal to the slope of the isocost, which is, all these isocosts have the same slope, right? Negative wage rate divided by the rental rate. So optimal combination of inputs, we are looking for best capital labor combinations. These will minimize total cost by producing a given level of chosen level of Q. So in our case it was Q0, we assumed that was profit maximizing. By choosing the input combination capital labor on the isoquant for which Q is tangent to the isocost curve. Basically saying exactly what we talked about. Two slopes are equal in equilibrium, which implies that the marginal product per dollar spent of the last unit is for the input is the same. So remember the condition, marginal product of labor divided by marginal product of capital. This was the slope of the isoquant and slope of the isocost, right? Get rid of these negative signs. I'm just going to change the locations of these two. Nothing will change. So marginal product of labor, I'm going to move this thing to the denominator, wage, equals moving marginal product of capital to the numerator on the right hand side, divided by R. Same thing. This is a very powerful expression. This basically says that choose your labor and capital such that each dollar you spend on labor, let's say this right hand side tells you each dollar you spent on labor, let's say, brings 5 units of output, and each dollar spent on capital needs to bring 5 units of output. That's why you become that's how you get to equilibrium. So basically, if I spend $1 on labor, the left hand side English translation is, if I spend $1, let's say I have $1, if I spend, oops, I'm so sorry. I have $1, right? I have $1. And if I spend that $1 on labor, this is how much output I'm going to get. How much one worker produces divided by how much I'm paying this worker. So if I spend my one last dollar on labor, this is how much output I'm going to get. Maybe I'm going to produce 5 units of output. And right hand side tells you if I spend my $1 on capital, how much more my output is going to increase. So what we're looking at is that at equilibrium, at the best optimal level, we're looking at the equality of these two things. So last dollar you spend on labor brings you quantity that you get by spending $1 on labor equals to the output you get, and see an increase in output you get when you spend last dollar on capital. So I'm going to talk about this. What if this was unequal, right? So marginal product of labor, let's change this color. So what if it was such that marginal product of labor, what if we had this? So this inequality means that if I spend $1 on labor, I get more output than if I spend my last dollar on capital. Therefore, I need to hire more labor. We're not doing optimal. As you hire more labor, marginal product of labor will go down, diminishing marginal productivity, and marginal product of capital will go up. Why? Because capital will become more productive as you hire the other input. So this inequality, this side will go down, this side will go up. So this inequality will become an equality. Okay? So let's take a look at this one. Sorry about screaming. So this is optimal input combination to minimize cost for a given output. So this is what we have been doing, profit maximizing company. So assume that this company wants to produce 10,000 units, okay? There are different ways to produce this. For instance, K prime, L prime line, that's it, one way to produce, and points A and C are on this line. K double prime, L double prime line, look, this point B is on this line. I thought there was one line, no. And K triple prime and L triple prime, this point E on this line, on this isocost line. We are trying to produce this at the lowest possible cost. This is the lowest. This is a little bit more expensive. This is the most expensive. So by definition, optimal level will be at point E is optimal. So optimal level of capital and labor, I'm going to put stars because that tells you the best level of input combinations. So that's going to be 60 capital and 90 units of labor. Actually, in math, we write x-axis first, so let's keep it that one. It's okay. So L star x, K star y. So 90 units of L and 60 units of capital. That's it. Okay, so that's optimal. So it's your job right now, folks. We're going to make these assumptions. Assumption number 1. Wage rate is 40, rental rate is 60. Okay, I know from the graph E is the optimal level. Okay, so given these, okay, I want you to calculate the cost, right? Cost at point A. Okay, at point A, you have labor capital combination, right? At point A, I'm using 60 labor, 500 capital. This is your exercise. At point B, it's not given, but it is going to be more. All right, so let's calculate point C. Okay, point C, you have 150 labor and 40 capital. And point E, let's also calculate point E, which is 90, 60. So let's go ahead and calculate the total cost for all these points, and for wage rate 40 and rental rate 60. So I'm going to show you something real quick. If you go ahead and calculate, what you'll find, right? But please do that. What you'll find is point E has the lowest cost for this level of output. So by definition, right, isoquant, we're finding the isocost that's tangent to it, and point E only at one point. Okay, so this is little different. All right, so this is output maximization. This is not done very often, but this is different. This is not what we do. This is a rare case. This is output maximization for given level of cost. This really happens for nonprofit organizations. They have a fixed budget. They cannot change this. So they're stuck with this budget line, this KL budget line. So what they can do is that I have fixed budget. I am trying to maximize my production given the budget. So let's say I have a nonprofit animal shelter. So quantity could be number of animals that are rescued, right? So I have a budget. Let's say I have $500,000 budget, which is very good, generous. So I'm trying to find the maximum number of animals that I can rescue. So in this case, we're trying to find the isoquant, blue isoquants, and I'm trying to go to the highest isoquant because I want to produce the maximum. I want to say the maximum number of animals, 1700 versus 1000 versus 500. Okay, because I can spend the same money but only say 1000 animals. However, this is not efficient at point S. Point E is a better point. I could spend all the money, this budget line, and I only can say 500 animals. Point R is not efficient. This combination is efficient. And let's talk about the expansion path, optimization and cost. Expansion path is a locus of points or a curve that shows cost minimizing capital and labor combinations for each level of output. Okay, so this is derived for a specific set of input prices. So your wage rate is fixed. When I put a bar, that means it's fixed. Your rental rate is fixed. Okay, so input prices are fixed. What's the optimal level of inputs if I produce, let's say, 1000 cars a day, let's say 2000 cars a day? Let me tell you something. These inputs will not increase proportionately because you're increasing your production twice as much, right? You're doubling it. That doesn't mean you have to double these, right? Along the expansion path, the input price ratio, WR ratio, is constant and equal to the marginal rate of technical substitution, which is also the same. So let's take a look at an example of an expansion path. So this is the level where I want to produce 500 units of output. Point A gives me the optimal capital labor input combinations, 118 and 91 labor and capital respectively. If I increase my production by 40%, so this is a 500 to 700 increase, right? So what's going on here is that what you're seeing here is that now the optimal point, I'm moving to a higher cost isocost curve, right? My costs are going up. I can't really produce 700 units using KL isocost curve. So I'm moving to a higher isocost curve. Optimal combination is at point B now, which uses 148 labor and 126 capital. All right, so I'm combining these 2 points. Let's go to the next output level we wish to produce. So let's say profit maximizing output level is 900. Okay, I need to definitely increase my production level. All right. So to increase that and do it at the minimum cost, I find the tangency point between this isoquant and the isocost, boom, at point C. Okay, and here I'm using 200 workers, 150 capital, and I connect these points. This expansion path doesn't have to be a straight line because things don't need to be increased proportionally. So this concludes part 3. I'll see you in part 4.